Welcome back to the deep dive. Today we're tackling a really interesting one, solar power.
That's right. We're digging into Lecture 10 from Professor Ghosh's Renewable Energy Resources course. Lecture 10 is crucial. It covers how solar radiation actually hits the Earth and starts introducing solar thermal concepts, basically, using the sun's heat. Our aim here is really just to spark your interest. Professor Ghosh goes much deeper.
But first things first, you really need to grasp how Earth and the sun interact to understand how to capture that energy properly.
It's fundamental. It's way more complex than just, pointing a solar panel somewhere sunny.
Okay, let's unpack that complexity then. Starting with something maybe not obvious, the Earth's tilt. It's not perfectly upright, is it?
No, not at all. The Earth spins on an axis tilted about 23.44 degrees relative to its orbital plane, the path it takes around the sun.
Huh. 23.44 degrees.
And what's really wild is that angle isn't even fixed over geological time. It wobbles a bit over thousands of years.
Wow. So how does that tilt? How does it actually complicate using solar energy? What's the key takeaway?
Well, the big thing is that tilt is why we have seasons. It dictates how much direct sunlight different parts of the Earth get throughout the year.
Right, so it makes solar energy much more variable depending on location and time of year.
Exactly. A fixed panel won't get the same energy input day in, day out, or month in, month out. It changes. Professor Ghosh also mentioned the celestial equator.
Yeah, that sounds pretty astronomical. How does it fit in?
Imagine Earth's equator projected out onto the sky. That huge imaginary circle is the celestial equator.
Okay.
Because Earth is tilted, this celestial equator is also tilted relative to our orbit around the sun. It's like our tilted frame of reference in space.
So the poles are constantly changing their orientation to the sun because of this tilt.
Precisely.
Got it. So the tilt creates the variations. Now, how do we pinpoint where on Earth these variations are happening? That's latitude and longitude, right? Quick refresher.
Absolutely. Latitude lines run parallel to the equator. They tell you how far north or south you are. Think of them as circles getting smaller towards the poles.
And longitude.
Longitude lines run from pole to pole, perpendicular to the equator. They tell you how far east or west you are from a starting point, the prime meridian in Greenwich, London.
So does that mean places on the same latitude generally have similar solar experiences?
Broadly speaking, yes. They'll have similar lengths of day and night through the year, similar sun angles, that sort of thing. Local weather obviously plays a big role too, but the baseline solar pattern is similar.
Okay. And Professor Ghosh mentioned dividing Earth into 4 quadrants based on the equator and Greenwich.
Yeah, that's just a convention for coordinates. North latitude is positive, south is negative. East longitude is positive, west is negative. It's just a simple way to give every spot on Earth a unique address using numbers.
Makes sense. So tilt, location. Now the Earth's journey around the sun brings us equinoxes and solstices. Big milestones in the solar year, yeah.
Huge. Because of the tilt, there are 2 points in the orbit where that celestial equator we talked about crosses the plane of Earth's orbit.
The equinoxes.
Exactly. Vernal around March 21st, autumnal around September 23rd. The key thing is, on those days, the sun is shining almost directly over the equator.
Resulting in
Roughly equal day and night pretty much everywhere on the planet. Equinox, equal night.
Nice mnemonic. Okay, equal day and night. What about the solstices then? They sound like the extremes.
They are the extremes. Take the winter solstice around December 21st for the northern hemisphere. That's when the northern hemisphere is tilted most away from the sun.
Giving us our shortest day, longest night.
Correct. And at that moment, the sun's most direct rays are hitting 23.5 degrees south latitude, the Tropic of Capricorn. The Arctic Circle gets 24 hours of darkness. The Antarctic gets 24 hours of light.
Wow, complete opposites. And summer solstice.
Flip it around. June 21st, roughly, northern hemisphere tilted towards the sun. Longest day, shortest night up north.
And the direct sun is now hitting.
The Tropic of Cancer, 23.5 degrees north latitude. Continuous daylight inside the Arctic Circle. Continuous darkness in the Antarctic. It all comes back to that 23.44 degree tilt.
Really highlights the impact. Okay, next concept. The declination angle. What's that measuring?
The declination angle, often written as delta, is the angle between the Earth's equatorial plane and the line connecting the centers of the Earth and the sun.
So it's like how high the sun appears relative to the equator on any given day.
That's a good way to think about it. Yes.
Yeah.
It tells you how far north or south the sun's direct rays are falling.
Oh.
And this angle changes constantly through the year.
Swinging back and forth with the seasons.
Exactly. It goes from a maximum of about plus 23.5 degrees near the summer solstice.
Sun highest in the northern hemisphere sky.
Right. down to about negative 23.5 degrees near the winter solstice.
Sun lowest.
And it's 0 degrees exactly at the equinoxes when the sun is directly over the equator.
Professor Ghosh gave an equation for this. Sin delta equals 0.39795 cos 0.98563 N173. Where ends the day number? Looks complicated. What's the real point of it?
Yeah, the math can look a bit intense, but the key insight is simply that we can predict the sun's apparent north-south position very accurately just based on the day of the year.
It describes that yearly cycle mathematically.
Precisely. And Professor Ghosh noted if you plug in N173, which is around June 21st, the summer solstice,
You get delta equals about 23.5 degrees.
you got it. The formula works beautifully. It's a predictive tool.
Okay, so if we know our latitude and the day's declination angle, how does that tell us how high the sun is in our sky? That's the solar elevation and zenith angles, right?
Exactly. Let's use his example. Chicago, latitude about 41.8 degrees north. Now, imagine it's the vernal equinox. What's the declination?
0, right, equinox.
Perfect. So, picture standing in Chicago. Straight up is your zenith. A flat plane around you is the horizontal.
Okay.
The zenith angle is the angle between that straight-up zenith line and the direction of the sun's rays. On the equinox, it turns out the zenith angle is just equal to your latitude.
So 41.8 degrees for Chicago at the equinox.
Yes. Now, the solar elevation angle, often called alpha, is the angle between the horizontal plane and the sun's rays. It's how high the sun is above the horizon.
Then how do we find that?
Simple geometry. The zenith angle and the elevation angle always add up to 90 degrees. So for Chicago at the equinox, alpha 91.8 equals 48.2 degrees.
Got it. Higher elevation angle means more direct, intense sunlight, which is what we want for solar power.
Absolutely.
So how does this change for Chicago at the solstices? Summer first.
Summer solstice, declination is about plus 23.5 degrees. The zenith angle is roughly latitude minus declination. So 41.8, 23.5 equals 18.3 degrees.
A much smaller zenith angle.
Meaning the sun is much higher. The elevation angle, alpha, becomes 18.3 equals 71.7 degrees. Much more direct sunlight, hence summer heat.
And winter solstice in Chicago. Brr.
Declination is about negative 23.5 degrees. The zenith angle is latitude minus the declination, so 41.8 negative 23.5.
Which is 41.8 plus 23.5.
Equals 65.3 degrees, a huge zenith angle. The sun is very low.
So the elevation angle is only 65.3 equals 24.7 degrees.
That's right. Very slanted sunlight spread over a larger area, much less intense. Winter chill explained, basically.
These angles are clearly crucial. Okay, what about the hour angle? What does that add?
The hour angle, omega, tracks the sun's movement across the sky during the day due to Earth's rotation. It's defined relative to local solar noon.
Solar noon being when the sun is highest in the sky.
Exactly. At solar noon, the hour angle is defined as 0 degrees.
And how does it change from there?
Well, the Earth rotates 360 degrees in 24 hours. That's 15 degrees per hour. So the hour angle is calculated as omega equals 15 times T12, where T is the local solar time on a 24-hour clock.
So before noon, T is less than 12 and omega is negative.
Yep, and afternoon, T is greater than 12, omega is positive.
Yeah.
It essentially measures the sun's east-west position relative to its peak at noon.
Okay, a time-based angle. Now, can we put it all together? Declination, latitude, hour angle to find the sun's elevation at any specific time.
Yes, there's a key equation for that. Looks like this. Sin alpha, sin delta, sin phi, plus cos cos. Delta cos phi.
Whoa. Okay, break that down. Alpha is elevation.
Delta is declination, phi is latitude, omega is the hour angle.
So this connects location, phi, time of year, delta, and time of day, omega, to tell us the sun's height, alpha.
Exactly. It's a really powerful formula in solar energy calculations. It lets you predict the sun's position precisely.
And Professor Ghosh stressed how vital this is for optimizing solar devices, right? Especially trackers.
Absolutely critical. If you want maximum energy capture, your solar collector needs to face the sun directly. This equation, along with calculations for the sun's azimuth, its compass direction, which we haven't detailed, allows engineers to design systems that track the sun perfectly across the sky all day, all year.
Amazing. Okay, so that covers the fundamentals of the sunlight reaching us. Professor Ghosh then pivoted to how we use that energy. He mentioned two main forms.
Right. Thermal energy, basically heat, carried mostly by longer wavelengths like infrared and light energy, or photons, which are the particles of light, especially in the visible and UV spectrum.
Let's start with the photon applications. What relies directly on the light particles?
Well, the most fundamental example he gave is photosynthesis. Plants using photons to create energy, the basis of almost all life.
Can't argue with that.
Our own eyesight works by photons hitting our retinas. And technologically, the big one is photovoltaic panels, or solar cells, which convert photons directly into electricity.
Okay, light interacting directly. What about using the sun's heat, the thermal applications?
There are tons. The biggest natural one is the Earth's water cycle. Solar heat drives evaporation from oceans, lakes.
Creating clouds, rain.
Exactly. That evaporation stores energy. He even mentioned how this relates to potential energy in rain clouds or even pumped hydro storage. Other uses include solar-powered refrigeration, which sounds counterintuitive but works.
Heat to make cold.
Yeah, using absorption cycles. Also, desalination, purifying water using heat. And of course, traditional uses like drying clothes or crops.
He mentioned a holy grail, solar water splitting.
Ah, yes. Using sunlight directly to split water, H2O, into hydrogen, H2, and oxygen, O2. Hydrogen is a clean fuel.
So if we could do that efficiently.
It'd be revolutionary. A clean, potentially limitless fuel source powered directly by the sun. He also touched on using solar energy for chemical synthesis, making materials without fossil fuels. Huge potential there, too.
Definitely sounds like future tech. Back to established thermal uses, he talked about direct, diffuse, and concentrated radiation.
Right. Direct is the sunlight coming straight from the sun in parallel rays, what makes sharp shadows.
Huh.
Diffuse is sunlight scattered by clouds, dust, air molecules. It comes from all parts of the sky, which is why you can still get sunburned on a cloudy day.
And concentrated.
That's when we use mirrors or lenses, like a magnifying glass, to focus the direct sunlight onto a small area. This bumps up the intensity and temperature significantly.
How are these used in practice?
Well, agriculture uses trapped heat in greenhouses. Solar pumps move water. Simple solar lanterns provide light. Solar cookers use concentrated heat.
Water treatment.
Solar disinfection, SODIS, uses UV photons mainly, but also some heat, to kill microbes. Solar stills use thermal evaporation for desalination. Even buildings use passive solar heating and integrated PV.
It's way broader than just PV panels. He also made a point about India's history in solar thermal.
Yeah, that was interesting. Apparently, from the 1950s to the 70s, India was a real leader in solar thermal research.
But then the focus shifted.
It seems so. More recently, the global push has been heavily towards photovoltaics, maybe overshadowing some really valuable, simpler thermal applications, what he called the low-hanging fruits.
And one big example of that was traditional salt production. How is that solar powered?
Massively solar powered. India's long coastline and sunny climate are perfect for it. You basically pump seawater into shallow ponds called salt pans.
And let the sun do the work.
Exactly. The sun's heat evaporates the water. Since seawater is only about 3.5% salt, you need to evaporate a lot of water.
It must take ages.
It does. And as the water gets more concentrated, different minerals start to crystallize out. It's called fractional crystallization. Gypsum often comes out first.
Useful for cement, he mentioned.
Right. Then eventually, the main target, sodium chloride common salt, crystallizes and is harvested.
What's left over?
A super concentrated brine called bittern. And that's not waste either.
No.
It's rich in other valuable things like potassium salts, potash, bromine, magnesium compounds. You can recover those through further solar evaporation or other processes.
So it's a whole sequence powered by the sun. He mentioned India producing 35 million tons of salt this way.
Yeah, a huge amount, almost entirely thanks to solar energy. Places like the Rann of Kutch are like giant natural evaporation basins. They recover salt, bromine, potash there.
Fascinating. So what makes a place good for these kinds of solar evaporation processes?
Obviously, lots of sunshine is number one. Low humidity helps evaporation happen faster. Wind can actually help too, surprisingly, by carrying away the moist air.
What else?
The ground needs to be pretty impermeable. You don't want your valuable brine seeping away. And you need easy access to the raw material like seawater or inland brine sources.
Okay. He then moved on to something called solar ponds. Sounded quite clever.
Very clever. A solar pond is designed to collect and store solar heat in water. The trick is creating a salt gradient.
Meaning?
You have very salty, dense water at the bottom and progressively less salt, less dense water towards the top.
How does that help?
Sunlight penetrates through the clearer top layers and heats the bottom layer, which is often dark-colored, to absorb more energy. Because the bottom layer is so dense, it resists rising through convection. The less dense layers above act like an insulating blanket.
Trapping the heat at the bottom.
Exactly. You can get temperatures of 70, 80, even 90 degrees Celsius down there. Then you can extract that heat using pipes and heat exchangers for industrial processes or other heating needs.
Where did this idea come from?
Pioneered in Israel, but India, through scientists like Dr. Data, was an early adopter too. They need careful construction. Low seepage, dark bottom, maintaining the gradient, sometimes rings on top to stop wind mixing the surface. He even suggested slanting the pond bottom could capture more sun.
Cool concept. Another water-related one, solar stills for desalination, making fresh water from salty water.
Yeah, it's like a mini water cycle in a box. You have a shallow basin, usually painted black, holding the saline water. It's covered with a sloping sheet of glass or clear plastic.
And the sun shines through the glass.
Right. It heats the water in the black basin, causing evaporation.
Yeah.
Water vapor rises, hits the cooler underside of the sloping glass,
Condenses.
and trickles down the slope into a collection channel. Pure distilled water. He mentioned a big early one in Chile. It's simple, low-tech, great for remote sunny areas.
What are downsides?
Efficiency isn't super high. You need a decent area to get significant water. Scale buildup in the basin can be an issue. The temperature difference between the water and the glass cover matters. Wind can cool the glass too much, but it's a robust technology.
Makes sense. Then solar dryers safer than just leaving fish out in the sun, like his Sunderbans example.
Definitely more hygienic.
Huh.
Open-air drying attracts flies, dust. Solar dryers enclose the food. The simplest use natural convection. A black surface heats air.
Yeah.
The hot air rises through the food chamber, carrying moisture away.
Can they be improved?
Oh yeah. You can add reflectors to boost the temperature or use a small PV panel to power a fan for forced convection, much faster drying.
It's about controlling the process.
Exactly. Understanding drying curves, how fast moisture leaves grapes to become raisins, for instance. You can even recycle the hot, relatively dry air coming out to make it more efficient. Or use humidity sensors and automated vents. Even add drying agents at the air inlet. And briefly, solar cookers. Simple idea. An insulated box, black inside to absorb heat, often with a reflective lid or panels to focus more sunlight into the box. Cooks food slowly but effectively, using only sun power. Again, potential for improvement and wider use.
Okay, finally, he introduced concentrating solar technologies. These are for really high temperatures, like power plants.
Yes, instead of just heating water a bit, these use large mirrors to focus sunlight intensely onto a receiver, getting temperatures high enough hundreds of degrees C to make steam and drive turbines for electricity. The key shape here is often the parabola.
Ah, parabolas, back to geometry. He gave the equation y = 1 4 f's 2. What's the f?
F is the focal length. It determines how deep or shallow the parabola is. A bigger f means a flatter curve.
And why is the parabolic shape so important?
Because of its unique optical property. Any parallel rays of light, like sunlight arriving from the distant sun, that hit the inside reflective surface of a parabola will all bounce off and converge at a single point.
The focal point.
Exactly. It concentrates all the light energy hitting the mirror onto that one tiny spot, creating incredibly high temperatures.
Like a perfect funnel for light. He also mentioned the directrix.
Yeah, that's a related geometric line. The definition of a parabola involves the focal point and the directrix. Every point on the parabola is exactly the same distance from the focal point as it is from the directrix, measured perpendicularly. This underlying geometry is why it focuses light so perfectly.
Clever stuff. And for the long troughs used in power plants, what are the key dimensions?
You have the length of the trough, obviously, then the aperture, which is the width across the opening, how much sunlight it intersects.
And the rim angle.
The rim angle helps define the curvature. It's the angle from the focal point out to the edge, or rim, of the parabolic mirror, measured relative to the axis of symmetry. Keeping the rim angle consistent helps scale designs. In a trough, because it's a parabola stretched out, you get a focal line instead of a point.
So you put a pipe along that line.
Exactly. A pipe carrying a fluid, like oil or molten salt, runs along that focal line, and the concentrated sunlight heats it uniformly as it flows through. That hot fluid then carries the energy away to generate power.
It really is amazing how these geometric principles let us harness solar energy so effectively.
It absolutely is.
Yeah.
Understanding these fundamentals is key to designing better solar technologies.
Well, that was quite the tour through Lecture 10. We covered a lot, from the Earth's tilt and how sunlight varies, right through to the basics of thermal applications like salt making, desalination, and even high temperature concentration using parabolas.
Yeah, Professor Ghosh packed a lot in. It really shows the breadth of solar energy. It's not just PV panels. These thermal applications, some ancient, some modern, are incredibly important and often very cost-effective. We hope this gave you a good foundation and maybe some new appreciation for the power of the sun's heat.
So here's a thought to leave you with. Considering everything we've discussed about how sunlight hits the Earth and the different ways we can use its heat, what other, perhaps less obvious, solar thermal innovations might be really crucial in the future? especially thinking about specific places with unique climates or resources. Something to ponder. Thanks for joining us on the deep dive.